Bismillahirrahmanirrahim. Assalamu alaikum, dear student. And today the topic of our discussion is ionic bond in bonding in solids. So we have already discussed some of the salient features of the ionic bond. We have already discussed the special type of bondings in solids in details in previous lectures, along with the salient features of ionic bonding, including the ions and ionic radii of different molecules like sodium fluoride. And after the uh, ionic radii, we already discussed the ionic structures along with the general principles. Moreover, the radius ratio rules, and we'll also discuss how to find the radius ratio of different compounds like sodium chloride, cesium chloride, etc. Moreover, we already discussed the borderline radius ratios and distorted structures of molecules along with the latest energy of ionic crystals. And lastly, we already discussed the Kapsunski equations, and we also learned the importance of these equations. Now the topic of our discussion is the Born-Haber cycle and thermochemical calculations. The latest energy of a crystal is equivalent to its heat of formation from 1 mole of its ionic constituents in gas phase. For example, if we look at the equation stated here, the sodium positive ion is found in the gaseous state, while the chloride negative ion is also in gaseous state. They will combine together and form sodium chloride, but in solid state. And the delta heat, delta H, is equal to latest energy. We already discussed about the U. It cannot be measured experimentally. However, the heat of formation of a crystal, delta HF, which is the heat of formation, can be measured relative to the reagents in their standard states. For example, in this equation we can see that sodium solid form along with 1 by 2 chloride ion is actually this is only 1 chlorine. We need to take 1:1 ratio. Here we can see that in gaseous state they will combine together and change into sodium chloride, which is solid in nature and is equal to delta heat formation, delta heat of formation. So delta HF may be related to U, which is the latest energy, by constructing a thermochemical cycle which would be known as Born-Haber cycle, in which the delta HF, which is the heat of formation, is given by the summation of energy terms in a hypothetical reaction pathway. For sodium chloride, the individual steps in the pathway, commencing with the elements in their standard states, are as follow. We can see actually the sublimation of solid sodium. Solid sodium is found in the form of solid, and that would be equal to delta H, which is the heat of sublimation. HS, we can say HS, heat of sublimation. Ionization of the gaseous sodium ions, this is the ionization energy. And dissociation of Cl2 molecules into Cl1. So this is the dissociation energy we need to provide. Formation of Cl negative ion, actually this is the electron affinity. And coalescence of gaseous ions to give crystalline sodium chloride, which is the latest energy. Addition of these 5 terms is equivalent to forming crystalline sodium chloride from solid sodium and gaseous chloride as follow. We can see here. So this is actually the whole process is actually the here we can see this is the sodium positive sodium in solids form is actually This is the heat we need to the heat of sublimation, delta HS, and then it change into gaseous state, and after gaseous state it would be changed into ions, which is the ionizing power, and moreover same is the case with the chlorine. We have to dissociate 2Cl2 into 1Cl because this is only 1:1 ratio. So dissociation energy, then electron affinity, and change into chlorine negative, and then the U, which is the latest energy, and we will get the NaCl in solid form. If we talk about the from Hess law, we can get delta heat of formation is equal to sublimation plus 1 over D, which is the dissociation energy, and 1P and electron affinity plus latest energy. The Born-Haber cycles and the equation have various uses. For example, 6 enthalpy terms are present in this equation. There are 6 enthalpy terms present in this equation. If all 6 can be determined independently, then the cycle gives a check on internal consistency of the data. The values should be in kilojoule per mole for sodium chloride, which is as follows. This is the S sublimation IP and 493, ionization and the dissociation 121, and electron affinity, and U, which is latest, and delta heat of formation. Summation of first 5 terms gives a calculated value of delta H formation, and which is equal to minus 398.7 kilojoule per mole, which compares reasonably well with the measured delta heat of formation value of minus 410 kilojoule per mole. So if only 5 of the terms are known, the 6th may be evaluated using this equation that we this one. So an early application was the in calculation of electron affinities, for which the data were not then available. The stability of an unknown compound may be estimated. It is necessary to assume a structure in order to calculate U. Although there are obviously errors involved in choosing RE, these are usually unimportant compared with the effect of some of the other energy terms in this equation. So differences between U, which is the latest energy values obtained by the Born-Haber cycle, that is the thermochemical latest energies, and the calculated from the Ionic model of the crystal system may be used as evidence for non-ionic bonding effects. Data for the silver halides, for example shown in this table, for thallium and copper halides, which is not given, show that the differences between the two latest energies are least for the fluorides and greatest for the iodides. This is actually attributed to the covalent bonding in iodides, leading to an increase in thermochemical latest energy values. A correlation also exists between the insolubility of silver salts, especially silver iodide in water, and the presence of partial covalent bonding. Data for the corresponding of alkali halides show that difference between the thermochemical and calculated latest energies are quite small. Therefore, the ionic bonding model may be applied satisfactory to them. While covalent bonding is present in silver chloride and silver bromide, it is not strong enough to change the crystal structure from rock salt to 1 over the lower coordination number. Silver iodide is quite different, however. It is a polymeric and it is polymorphic and exists in at least three structures type, all of which have low coordination numbers, usually 4. Changes in the structure and coordination numbers due to increased covalent bonding are described later. I will discuss this at the end of the lecture. Certain transition elements have crystal field stabilization energies CFSC, which we have already discussed in detail in crystal field in inorganic material chemistry. So due to their d electron configuration, and this gives an increased lattice energy in their compounds. For example, the difference between experimental and calculated lattice energy in cobalt COF6 COF2 is 83 kilojoule per mole. In fair agreement with crystal field stabilization energy calculated for high spin state of cobalt in COF6 of 104 kilojoule per mole. Actually, the Bohr-Haber cycle has many other uses, that is in solution chemistry to determine the energies of complexation and hydration of ions. These usually require knowledge of the lattice energy of the appropriate solids, but since they do not provide any information about solids, they are not discussed further. So now we will talk about the stabilities of real and hypothetical ionic compounds. So first of all is the inert gas compounds. One may ask whether it is worthwhile trying to synthesize, for example, argon chloride apart from delta H formation, delta heat formation, the only unknown equation we already discussed. Suppose that hypothetical argon chloride had the rock salt structure and the radius of argon Ar positive ion is between those of sodium ion and potassium ion. An estimated lattice energy for argon chloride is then minus 745 kilojoule per mole. We know that the lattice energy of sodium chloride is minus 764, while potassium chloride is minus 701 kilojoule per mole. So the substitution of this equation may be yield this kind of data. ArCl have a large positive delta heat of formation calculated, and we would be thermodynamically unstable by a large amount relative to the elements. So such a calculation also tell us why argon chloride is unstable and cannot be synthesized. Comparing the calculations for argon chloride and sodium chloride, the instability of argon chloride is actually due to the very high ionization potential of argon, but the heats of formation calculated for several other hypothetical compounds are shown are shown here. A large number of inert gas compounds are now known following for example, the preparation of xenon platinum fluoride XEPTF6. Consideration of lattice energies and enthalpies of formation of these compounds to synthesize XEPTF6 by direct reaction of xenon and platinum fluoride gases. Some scientists had previously prepared O2PTF6 as an ionic salt. So from knowledge of the similarity of the first ionization potential of molecular oxygen and xenon. Someone realized that the corresponding xenon compound should be stable. So the next is the lower and higher valence compounds. Consider alkaline earth metals compounds. In these compounds, the metal is always divalent. Since a great deal of extra energy is required to doubly ionize the metal atoms, it is reasonable to ask why monovalent compounds, for example MgCl, do not form. Uh, because the data is given show that magnesium chloride MgCl is indeed stable relative to the elements, but that MgCl2 is much more stable. Uh, this is actually the example of this stability. In an in any attempt to synthesize MgCl, attention should be directed towards keeping the reaction temperature low or isolating the MgCl product in order to prevent it from reacting further or disproportionate. Similar trends are observed for other hypothetical compounds such as ZnCl, Zn2O, AlCl, and AlCl2. From the consideration of factors that affect the stability of compounds, the following conclusions may be drawn. Number one, the formation and stability of compounds with their lower than normal valence states are favorable when 1. The second and the higher ionization potential of metal are particularly high. The latest energy of the corresponding compounds with metal in its normal oxidation state is reduced. Number 2 is in order to prepare compounds with metal in higher than the normal oxidation state and during which it may be necessary to break into a closed electron shell, it is described to have low values of second ionization potential of the metal atoms and large latest energies of the resulting higher valence compound. As example of these trends, calculations for alkali and alkaline earth metals monohalides show that while all other unstable relative to the dihalides, the enthalpy of dispersion is least in each case of the iodide. On the other hand, the higher valence halogen compounds of group 1 elements are most likely to occur with cesium and copper subgroups in combination with fluorine. Thus, all cesium dihalides apart from cesium difluoride have positive delta heat of formation values and would be unstable. Cesium difluoride CsF2 is stable in principle with its great negative delta heat of formation value, but has not been prepared because its decomposition to cesium fluoride has large negative delta H. Uh, for example, silver dihalides delta heat of formation becomes less positive and finally negative across the series AgI2 to AgF2. This again shows that the effect of Re on latest energy and hence on delta heat of formation. Now the next example is about the copper halides. The copper halides are particularly interesting. The divalent state of copper in which the D10 shell of copper is broken into the most common state, and again dihalides show decreasing the stability across the series CuF2 to CuI2. CuI2 is actually appears not to exist, and its calculated delta heat of formation is barely negative. While in the monovalent state, the situation is reversed and all halides apart from copper fluoride CuF are known. CuF is calculated to be stable relative to the elements but not relative to the CuF2. These examples shows that several factors affect the formula and stability of compounds. Actually, the ionization potential, latest energies, and the relative stability of elements in different oxidation states. Often, a delicate balance between opposing factors controls the stability or instability of a compound, as with the copper halides. Detailed calculations are needed to assess the factors involved. Here is the effect of partial covalent bonding on crystal structures. Covalent bonding, partial or complete, occurs when the outer electronic charge density on an anion is polarized towards by any neighboring cation. The net effect is that an electron pair that would be associated entirely with the anion in a purely ionic state structure is displaced to occur between the anion and cation. In cases of partial covalent bonding, some electron density is common to have both atoms, but the rest is associated with the more electronegative atom. In purely covalent bonding, there is no distinction between cations and anions, because we know that bond formed by the mutual sharing of electron between the two atoms. The electron distribution in particular bond is symmetrical between the two participating atoms, and bonds are quite non-polar in nature. Non-polar covalent radii can be measured accurately and represent a point of reference with which to compare other radii. Thus, the atomic non-polar covalent radius of carbon given by half of the carbon-carbon single bond length is constant at 0.77 angstrom in materials as diverse as diamonds and gaseous hydrocarbons. Non-polar radii, however, are listed in this table. Some clear-cut examples of the influential of the particular partial covalent bonding on crystal structures of material, which might at first glance be expected as ions as follows. For example, strontium oxide, barium oxide, mercury oxide, strontium oxide, and barium oxide both strontium oxide and barium oxide both have the rock salt structure with octahedral M2 positive ions. If we talk about the size, based on the size considerations alone, and if it were ionic in nature, mercury oxide should have same structure. However, mercury is the only 2 coordinate in HGO. Linear OHGO segments occur and may be rationalized on the basis of sp hybridization of mercury. We know that the ground state of atomic mercury is, if we talk about the electronic configuration, then it should be the xenon 54, then 4f14, then 5d10 and 6s2. So if we talk about the first excited state, then it should be like xenon 54, 4f14, 5d10, 6s1 and 6p1. One of the electron in 6s is jumped from s to 6p. So this would be considered the first excited state of the mercury. Hybridization of 6s and 1 6p orbitals give rise to 2 linear sp hybrid orbitals, each of which forms a normal electron pair covalent bond by the overlapping with an orbital on oxygen. Hence, mercury has a coordination number of 2 in HgO. AlF3, Al aluminium trifluoride, aluminium trichloride, aluminium tribromide, and aluminium triiodide. So these show a smooth transition from ionic to covalent bonding as the electronegativity difference between the two elements decreases. Thus, aluminium trifluoride is a high melting, essentially ionic solid with the distorted octahedral coordination of aluminium 3 plus ions. It, its structure is related to ReO3. Aluminium trichloride has a layered polymeric structure in solid state, similar to that of uh, chromium chloride, which is related to the cadmium chloride and cadmium iodide structures. The bonds may be regarded as a part of ionic or covalent. Aluminium tribromide and aluminium triiodide have molecular structure with dimeric units of formula Al2XX. Halides of other elements, for example beryllium, magnesium, gallium, indium, also show variation in bond types and structures depending upon the halides. The trends are always same. The fluorides have largest value difference in electronegativity between two elements, and their structures are mostly ionic. Increasing covalent character occurs in series fluoride, chloride, bromide, and iodide. The occurrence of partial covalent bonding in an otherwise ionic structure may sometimes be detected by abnormally large values of lattice energy. In others, it is clear from the nature of structure and coordination numbers of atoms that bonding cannot be purely ionic. It is difficult to quantify the degree of partial covalence in a particular structure. Although chemist experts intuitively feel that most so-called ionic structure must have a considerable degree of a covalent character. Two atomic parameters that undoubtedly have a strong influence on bond characters are ionization potential, that is, the ease with which atoms ionize to form cations, this is the ionization potential, and electron affinity, that is, electron affinity is actually the strength with which atoms attract the electrons to form anions. So two other atomic parameters related to these that also strongly influence bond type are effective nuclear charge and electronegativity. Two approaches which have had considerable success in qualifying in ionicity are partial covalent bonding, and that use the concepts of sometime effective nuclear charge and electronegativity are the coordinated polymer of the Sanderson and the ionicity plots of Moser and Pearson. So we will talk about the electronegativity and partially charged atoms. The electronegativity of an atom is actually a measure of net attractive forces experienced by the outermost electron towards nucleus. Electronegativity originated by Pauling and is a parameter that correlates with the polarity and is surrounded by and bonded to several others. It illustrates how covalent bonds are initially non-polar may become polar due to electronegativity equalization. An alternative approach is to start with purely ionic bonds and consider how they may acquire some covalent character. In the ionic structure Mx, M positive, X negative, the cations are surrounded by anions, usually 4, 6 or 8. However, the cations have empty valence shells and are potential electron pair acceptors. Likewise, anions with their filled valence shells are potential electron pair donors. The cations and anions therefore interact in the same ways as do Lewis acids and bases. The anions with their lone pairs of electrons coordinate to the surrounding cations. The length and strength of this interaction, and hence the degree of covalent bonding which results, is again related to the electronegativity of two atoms. Thus, electronegativity electronegative cations such as aluminium 3 plus are much stronger uh, electron pair acceptor, which would be treated as Lewis acid, and then electropositive cations such as potassium. The coordinated polymeric model of structures proposed by Sanderson is actually based on this idea of acid-base interaction between ions and form a bridge between ion and the covalent extremes of bond types. This was all about the ionic bond. Thank you very much.